Good morning, good day, and good evening. Wherever you are, welcome to this PV Magazine webinar. My name is Marian Veloon. I'm an editor with PV Magazine and your host today. Mono or multi? That's a question for many project developers when it comes to inverter choice. In case they're using string inverters, which they're increasingly more likely to do, developers have the choice of an inverter with a single maximum power point tracker and an inverter that has as many as 32 such trackers. These devices can optimize energy yield for any given environmental condition, especially since temperature and irradiation intensity alter the voltage and current levels coming out of the semiconductor. For example, the voltage of a PV module goes up as the temperature drops. A high number of such trackers in theory promises higher yields because there's a higher granularity of optimization. In practice, it might all look a little bit different. Andreas Henser, team leader of power electronics at Fraunhofer Institute for Solar Energy Systems, investigated how big of a difference the use of multi-MPPT is. He and his team have modeled different sites at different locations in the world and with various numbers of MPPT trackers to see how much bigger the yield is. Welcome to the program, Andreas Henser. I'm curious to hear all about your findings in a few moments in this webinar. And the inverters. Okay. Hello, welcome. The inverter's MPPT approach also limits design flexibility, above all due to the short circuit current produced by modules. This limits how many modules can be connected in serial or parallel or how it should all go on. And with many modules recently having received updates to the short circuit current level, Boban Vujovic and Product Lifecycle Management and at Kaco New Energy and Ronak Shah, head of offers and applications, will explain why such considerations don't matter for string inverters with a single MPPT and why these inverters offer greater deal of system flexibility. Welcome, Boban, and welcome, Ronak.
Thank you. Thanks for having us.
Thank you. Yeah.
Thanks for being here. Well, before we jump right into the topic, please note that you can ask questions throughout this webinar. If you look to the right of this session, there's a tab, exactly, it says Q&A. I will receive the questions and I will feed them to our experts as we go throughout the webinar. I will do this for the entire duration of the webinar, but I will save a larger amount of questions for the end. So don't fret if I get to your question not right away. Speaking of questions, one question that we always get is whether you can have the recording of this webinar. And the obvious answer to this question is yes. And also we will make the presentations of this webinar available to you in a mailing that we will send around after the session has finished. Also, with regards to a recording, if you happen to be a German speaker, we have recorded this webinar before in German, or we've done it before previously in German. So you can go to pvmagazine.com, look at events, and in the events page for this webinar, you will find a link directly to the German recording. Otherwise, of course, you're more than welcome to stick around for the English version of this webinar, where we also might have some different insights. So far, that was that from my side. Housekeeping done, and with no further ado, I will hand it to you, Andreas.
Okay, everybody, then welcome from my side as well. I'm happy to be here and to be able to share with you some results of a study that we performed on behalf of Kaco New Energy. And the basic question of the study was how much yield gain is possible with multi-MPPT inverters. And for this study, we analyzed different plant configurations and locations and tried to simulate how much yield gain is possible for different conditions. I'd like to motivate you with this slide. I think everybody of you would agree on the statement that the market share of large string inverters is increasing a lot during the last 5 years. So if everybody of you that attended a fair trade for PV systems in the last year, for example, the Intersolar, could see that almost on every booth of our power electronic manufacturers, you will find a system that could be classified as a large string inverter. And the reason we tried to analyze the complete market in order to prove that this is not only a subjective opinion, but is really corresponding to what is happening on the market. So we analyzed the data sheet of the biggest manufacturers that you can find in the PV market, and we saw that from in the power range or a power class above 100 kVA, that we found 44 devices that could be classified as standard wall-mounted string inverters. And out of these inverters, out of these 44 inverters, 36 do provide the user with multi-MPPT inputs, whereas only 8 do have a single MPPT input. An additional remark here is that the Kaco devices were not included here. So with the Kaco devices, the numbers would change a bit because the Kaco devices do provide a single MPPT in that case. I have prepared this agenda for you, so I will start with some basics of multi-MPPT and mismatch losses. I will then summarize the investigated scenarios and effects in our study. We'll tell you something about the simulation conditions that we applied, and then I will come to some results and close with a summary and outlook. So the basic difference is the number between single MPPT and multi-MPPT inverter is the number of MPPT inputs. So for example, if you have a look on the left part of my slide, you see that for single MPPT inverters, all module strings, PV module strings, are simply connected in parallel and then connected to the inverter. That is the reason that in most cases you will have a single stage topology inside the inverter, and it had the drawback in that case that the minimum input voltage of the inverter, DC input voltage, is defined with the AC output voltage that you would like to have. And in comparison to that, for multi-MPPT inverters, you have different inputs where you can connect to each input 1 or 2 strings in parallel. And therefore, the MPP tracking for each of the 1 or 2 strings is decoupled from each other. And also the DC input voltage is decoupled from the AC output voltage. So it gives you the ability to independently do your MPP tracking and therefore to reduce mismatch losses. And also it has the advantage that the minimum input voltage is independent of the AC output voltage, which gives you a wider window for the input voltage of your inverter system. So what does mismatch mean? I think these curves is well known by most of you. In this graph, I have drawn VI curves and PV curves for a standard module. And I have applied different irradiances. And what you can see here is that the MPP point differs with the irradiance in that case. So the blue curve is for 100 watts per square meter at 50 degrees, and the orange curve for just 200 watts per square meter. And when you do independent MPP tracking, then the complete power of the system is just the sum of the 2 powers that can be drawn out by each of the strings. But if you have only a single MPPT input and you parallelize these 2 strings, you get a resulting curve that corresponds to, in this example, to the green curve here. So the MPP point is somewhere in the middle between the MPP points, and you will have mismatch losses. In that case, in our example here, we have a mismatch loss of 0.18%. And this mismatch loss can be compensated by multi-MPPT inverters. And the big question is, how big is that effect for different configurations and locations? And we tried to answer this question from the technical point of view. Before we started, we analyzed and defined different effects that are leading to mismatch losses over the time in a PV plant. Today I will only be able to show you some results of 4 of these effects. So I will focus myself on shading effects and on heterogeneous string configurations and of the impact of the voltage threshold, so the minimum input voltage of an inverter. But the complete study is public and can be downloaded. The link is on my last slide. So if you're interested, yeah, you can download the full study in order to see the analysis of all the effects. We defined 2 different basic scenarios. So the first one is a rooftop system with 1000 volts system voltage based on 60 kVA blue planets. This inverter has only a single MPPT, but we created a synthetic model out of the parameters of that inverter with multiple inputs, in that case 6. And we did the same for scenario B, which is referred to as the ground-mounted system. So the difference is that we have a bigger inverter, so it's a Kaco Blue Planet 165 that we have chosen as a basis, and in that case we we spent 9 MPPTs for the synthetic module in order to do the difference between single and multi MPPT here. And
Yes,
these scenarios, yeah.
My apologies. I thought you were finished with this slide, but please go on. Then I have a question for the previous slide for you.
Okay.
Yeah.
So these scenarios were the basis, or are the basis for our study, and with this basis we performed yield simulations over a year for different locations and had a look of how much the difference is with multi-MPPT and single MPPT. So, Marianne.
No, my apologies again. I think there's a question to the slide you had previously, and that was to ask how you calculated the mismatch losses without flash data. I think it was the one before that even.
Yeah, so I will come later to that point. So the software that we used is PVSYST, and in PVSYST you get data for different commercial products, different modules, and by this data and the single diode model, the curves are created, and by this we have calculated the mismatch losses. And but I will also show you later the problem about that. So so maybe the question is a bit too early, so I will come back to that in more detail later.
Thanks for answering this question, and to the audience, please continue to keep posting your questions. I have a first few, but I'm looking forward to reading more of your questions, and this is your chance to ask the experts.
Okay. Okay, then I continue, and it's also is really referred to that question that you mentioned. So yeah, we decided to use a standard simulation environment that is used by a lot of people around the world to do yield simulations. And in this software, you have a big data source or data set for different manufacturers, different modules, which you can easily integrate in your system, and then you get quite easily results for your system. And inside the program, every module is modeled in the way that the single diode model is used. And we had, before we started, a closer look on that because we were not sure if this model is really reflect or representing the module correctly, today's module. So we did a comparison between measured data in our accredited test lab at Fraunhofer ASE and the model data that we got from PVSYST, which comes normally from the manufacturer. And you see here the first differences. So these are 3 different curves at different irradiances and different temperatures. And we see that the model which is used for the simulation is worse is better than the data that we got from our measurement. So that was one of the first thing that we saw. But in fact, okay, for the results of our study, it's not so important, but what we did in order to prove that, we did a refit with the measurement data and compared then the two curves. So on the right side, you see a refit with data that we measured, and then we remodeled the module with the refitted values, and you see that the single diode model is really good representing the complete curve of the module. So our conclusion is that today's modules are very well modeled with the single diode model that is used in PVSYST. But what is questionable from our side is the reliability of the data, but the influence of the results of the study are not affected by this. So we continued with PVSYST, but it's just a general remark from our side. And we heard that also from different customers, because we have this accredited test lab at Fraunhofer ISE, that in some cases the data seems questionable that you get from data sheets and manufacturers. And the second point that we analyzed in advance is that PVSYST is modeling the yield by with a resolution of hourly value of the meteo data. And what you can see on the right is that for a sunny constant day, the data or hourly values are good representing what is happening on the system over the day. So it's just an example day out of 2016. But when you have a cloudy day with a lot of wind, then the irradiances can change quite quickly. So if you are only using the mean values, the hourly mean values, then you might get different results if you compare this to a higher resolution. And in order to evaluate that, so the conditions of the meteor data, we have built our own model in Python where we can integrate a higher meteor resolution, and we used meteor data that we collected here in Freiburg, which we have in a resolution of 1 minute values. And then we had, or we did more or less the same that PVSYST is doing over a year for a standard year, or for the year 2016 in Germany. And we analyzed how much losses we got from the different limits that the inverter have. So the one of the limit is the minimum power of the inverter, the other one the maximum power, minimum voltage of the MPP voltage, and maximum voltage of the MPP voltage. And we saw that the time resolution leads to different results. So what you would expect from the graphs above is represented by the results that we got. For example, the yield loss due to the maximum power limit of the inverter is 0.25% for string lengths of 20 modules. There's a spelling mistake here, 20 modules. And if you go with a time resolution of hourly values, then this is almost neglectable. Then you get only 0.1%. What we also see is that the losses due to the minimum power and minimum voltage, which is strongly related to our question regarding the difference between multi-MPPT and single-MPPT, is neglectable in our case. So the losses here, even at time resolution of 15 minutes values or 1 minute values, is below 0.01%. So this simulation is done with the new module, so with the weight data from the data sheet. So you might mention now that, okay, what about aging? Because all the parameters will age with time. So we analyzed this also, and we applied a statistical model with a yearly aging of 0.5% per year for voltage and current of the module. And of course, the losses due to Pmin and Vmin are increasing, but even after 25 years, they are only reaching 0.1% of losses overall in the last year after 25 years. So our conclusion was that PVSYST with our resolution could be used or can be used for analyzing this effect. And one additional remark before coming to results is that we excluded the efficiency losses of the inverter in our study. So we are always only talking about the theoretical possible additional yield at the DC terminals. The reason for that is that on the one side, all commercial inverters the efficiency of commercial inverters are quite close together. That's one reason. You see that here in the graph that on the left side, the single MPPT inverters, the worst device compared with the best device, difference is only 0.5%. But the other and the main argument is that this efficiency data is also coming from the inverter manufacturers. So we are having more or less the same problem that we got with the PV modules, that the accuracy of the data and the reliability is not 100% given, I would say. So we decided not to include this. We did also measurement. So we have also a test lab, accredited test lab for power electronics here at the Institute, and we compared measurement values under standard conditions with the data from the data sheet, and we saw also here that the data sheet is representing the inverter at 0.3% better or 0.4% better than the data sheet, and therefore we did this with two different manufacturers and two different devices, and we're always getting something in that range. So next slide is showing first results. In that case, we integrated an inhomogeneous PV generator configuration for a plant. So it's in that case based on scenario A. So we have 8 strings, each consisting of 18 modules in that case, and we varied the string lengths from 18 to 19 modules, and also the number of string with the corresponding length. And we then calculated the yield gain that could be achieved with multi-MPPT inverters here. And on the bar diagram on the right, you see that in the worst case, so when half of the strings have 18 modules and the other half have 19 strings, that gives you the maximum losses that you get, and over 1 year the yield losses or yield gain with multi-MPPT is at 1% year. Next example is a shading example. So we constructed this theoretical system here. So we had a rooftop system with a defined angle here, and we placed a tree in front of the generator in order to see what is happening or how much losses are caused by the tree. And what you see here is that no matter if you are in Arkona, which is a location here in Germany, or Abu Dhabi, which is a more sunny place, the relative yield gain with multi-MPPT is also in that theoretical example only at 1% per year that you got. From our point of view, of course, this 1% is only referred at the maximum yield gain, theoretical at the DC input of the inverter. So because you would normally expect a worse efficiency for multi-MPPT inverters, this yield will reduced by higher inverter losses in multi-MPPT inverters in general. So this example can be considered from our point of view as a really theoretical example, because no one would plant a tree there. What is a bit more realistic and more important, I would say, is the two examples that are following now. The first one is row shading of ground-mounted system. So whenever you have a ground-mounted system, you have tables, and these tables are creating shadow on the other ones, and that way creating losses and also mismatch. And we analyzed for this scenario how much these losses are, how big, and the diagram here is showed for an example in Arcona, where we had or we designed tables with 4 rows each and 28 modules as a string per table. So that gives us a collector height of 4 meters, and we designed the angle was optimized for the maximum yield. So for Arcona is at 35 degrees, and then we varied the pitch distance between the rows, and you see that if you go from 16 meter, which is kind of the optimum distance regarding to shading losses, because then you have almost no shading losses, and you decrease the pitch by a factor of 2, you lose energy, and the energy loss that you have caused by shading is in the range of minus 5.5%. But what is always overestimated by people that have we seen in discussion is how much of this energy loss can be recovered by multi-MPPT inverters. And this part is only 0.17% here. So of course you lose energy because of the shading or the higher shading, but multi-MPPT in such a configuration allows you only to recover 0.17% of these shading losses. And yeah, if you we designed the same plant in Abu Dhabi, the mismatch that can be, or the mismatch losses are a bit higher in Abu Dhabi, so in the range of 0.2%, but they are scaling to smaller distances because the sun is the sun angle is quite steeper, and therefore you have a lot of smaller you have lower losses in that case. Another common application that we designed is a ground-mounted system with single-axis trackers around the north-south axis. Those systems do also have shading, and we analyzed also what is happening in such a plant. And therefore, we had the same basis, so 2 rows on each tracker with 28 modules, and then we reduced the pitch between the tracker systems. And also here, these results are for Arcona. When you go from a pitch of 10 meters down to a pitch of 5 meters, you will end up with more or less the same energy that could be recovered by multi-MPPT, which is only in the range of 0.19%. So it's basically in the same range than for fixed tilt, the fixed tilt configuration that I have shown you before. So so I think that some of you may be a bit surprised by the results. So I try to explain a bit so why the results are as they are. So most of the effects that are leading to a voltage mismatch are related to irradiance. And if you analyze the MPP curve or the PV curve of a module, then this curve is quite flat around the MPP. And in order to show that a bit more concrete, we have plotted the graph here on the right side. And you see when you deviate the voltage around MPP, in that case, it's relative deviation. So if you vary this at 1%, then the losses in power is only at 0.1%. And this is, from our point of view, the explanation of that the multi-MPPT in plants that we analyzed in this study are quite that the effect of the multi-MPPT is quite low here in that case. So as a summary, we think, or we found out in our study, that the single diode model represents today's modules sufficiently accurately. We found also out that the resolution of the weather data of hourly values is enough, so higher resolution does not change fundamentally the results. From our point of view, that the additional yield is in the range that it will be probably compensated by the poorer efficiency of multi-MPPT inverters. And yeah, so also one remark is on the reliability of the data for PV modules and inverters. From our point of view, it's not always meaningful to do comparison and decisions just on the datasheet values, because these values are coming from the manufacturer and can only be proved by specific laboratories. So we see for homogeneous systems no significant additional yield with multi-MPPT. For 99% of ground-mounted system, industrial and commercial systems, the yield gain is really low, as we have shown you here. If you have heterogeneous system with different string lengths or with complex shadowing scene, then of course it might be an issue. The restriction for the results is that we focused on crystalline silicon modules. Whenever you have another module technology, then the results may change. So that's something. So with this slide, I'm finished my presentation, I think. Yeah, so I'd like to thank you and my colleagues that have performed this study with me. And here's also the link for downloading the study. And I'm happy for questions, and thank you very much.
All right, then I guess we would carry on the presentation. Welcome again from our side, from Kaco New Energy, and let's go through on what are our views on that and how do single MPPT inverters benefit you in certain scenarios. So I'll start and then we'll follow my colleague Boban Vojovic. Yeah, so based on this presentation from Mr. Hensel, you would have assumed, or one could assume, that Kaco would now in future only develop single MPPT inverters. Right? It's more beneficial to do so with looking at the numbers, but that's not true. We look forward to continuously expand our portfolio of multi-MPPT inverters, but based on the study, looking at where a single MPPT inverter is more advantageous and where a multi-MPPT inverter is more advantageous, and give the choice or the possibility of the choice to the customer, to you, to decide when to choose which type of inverter, what is my application, and which inverter would suit me better. And a small guideline from us over here, a single MPPT inverter is more beneficial as per the study and as per our experience on homogeneous plants, which are large-scale utility plants. They are all the modules are facing the same direction. You have normally high DC to AC ratios, same type of module, same string length, and it's mostly homogeneous. There are no trees in between, no near shading. And that also applies to industrial rooftops or commercial rooftops, which we see nowadays on big warehouses or big factories. So these are also homogeneous rooftops or homogeneous PV systems where the yield gain by a multi-MPPT inverter is not visible. And that is not just because of the multi-MPPT and single MPPT, but also because a single MPPT inverter brings some advantages on the table. And that we'll see in the next slide over here. Like, why do single MPPT inverter have higher efficiency. Now, there are 2 points to that. One is the single MPPT inverters do not have a DC-DC booster, which eliminates one step of conversion within the inverter, and it also reduces the complexity. It the inverter doesn't lose efficiency at this step, and this step or this efficiency loss is also not that clearly visible on the OND files of the inverters when you do a PVC simulation. So again, as Mr. Hensel said, go check the OND files, check if they have 3 efficiency values, at what voltages, and how are they created before you compare the results. So that's good due diligence to be done on the data supplied to you. Another factor that affects the efficiency of our inverters is that they have like the series of 87 to 165 kilowatt that we have as a silicon carbide based MOSFETs. It's a new generation of semiconductor moving away from the silicon based semiconductors now to bring to silicon carbide, and we have now a proven and stable technology since 2017-18. Inverters running all over the world on this platform and successfully working as well. And this silicon carbide based MOSFETs offer much higher efficiency levels, not just the peak efficiency, but the Euro and CEC efficiencies are quite stable, flat throughout the power output ranges, which gives advantage of a full day. Like overall, during the day, you will have higher efficiency levels due to these two factors, compared to momentary mismatch gains from a multi-MPPT inverters, which are just when you have some near shading or something blocking your module, compared to stable efficiency gains. So these two factors bring out why on a homogeneous plant, on a larger rooftop, on simpler designs, a single MPPT inverter is better compared to a multi-MPPT inverter, which would be then suitable on complex projects with some near shading or some object blocking the modules, or when you have to use different string lengths in the same MPPT. Now, apart from this efficiency factor, there is also how you make your PV plant that could affect the results or the yields of the project. And for that, my colleague would take over and present the next couple of slides.
Perfect. Thank you very much, Ronak. So I'll take over from here. So what Ronak just presented are the advantages of a single MPPT inverter based on the inverter. So the power electronics within the inverter. I'd like to take one step back now and look at the PV plant design as a whole. And when we at Kaco New Energy talk about PV plant design, we talk about virtual central design, of course. And for any of you who are still not familiar with virtual central, what exactly that means, we've done a small comparison on the left-hand side of the slide here. On the top, we see the, let's say, traditional multi-MPPT distributed solution, where we have a multi-MPPT inverter installed in the PV field. The PV strings are connected directly to that inverter, and then our main cable run is based on AC cable to the AC station, where we then feed into the grid. In comparison, at the bottom, we see the virtual central design, where in the place of the multi-MPPT inverter, we have a DC combiner also installed in the PV field. The DC strings are connected directly to this combiner. Our main cable run is based on DC cable that goes to our single MPPT inverter, which is connected at the AC station, where we then have a very short AC cable to then feed into the grid. So this is the main difference between a decentralized multi-MPPT solution and virtual central. And now a few of the major points around this design. There are a couple, so we'll start with the CapEx savings, so the capital cost when I'm building my projects. So what we've found and what we've increasingly received as feedback from our customers, although I have the additional cost of a DC combiner, because my main cable run is based on DC cable and my AC cable runs are extremely short, I'm actually able to achieve CapEx savings of 8 to 10% for my project. We have done a white paper. We've created a white paper on this topic. There's a link, I believe, in the next slide, which you can download. And I think it's also important to note this saving of 8 to 10%. These figures are based on a snapshot that we did last year around May, if I'm not mistaken, when we wrote the white paper. At that stage, the material prices on the global market were already increasing, but they've increased again since then. So savings above 10% are certainly possible on the CapEx side. Moving on to the OpEx side of things, in terms of service and maintenance, this virtual central design, from its nature, as you can see in the bottom right part of the slide, all of my inverters are installed in very close proximity to the AC station, close together. This makes service and maintenance very easy because all of my inverters are in the one spot. And additionally to that, we have some Kaco service advantages that we offer that I will talk about in a couple of minutes that make maintenance even easier for our customers. The last and very important point in terms of the advantages of a virtual central design is the possibility to achieve higher energy yields. And here the main focus is the ability to shift cable losses from the AC side to the DC side of the inverter. And if we look at the next slide, we've tried to visualize this a little bit. When we talk about large-scale PV projects, utility projects, we generally have an overloading on the DC side. A DC-AC ratio of anywhere between 120 to 140% is relatively common nowadays. We've used 130 in this example. And what we see here, or maybe one point first, why do we overload these projects? Because although with a high DC-AC ratio, I'm going to have some clipping losses with my plants, it allows me to produce more power more often on the AC side. And this is, of course, a huge advantage when it comes to the business case of my project. And we see on the top illustration here with a multi-MPPT distributed design that I lose this overloading advantage relatively quickly in the PV field where I convert from DC to AC. At that particular point, I have 100% of my AC output, but then comes a really big or long cable run that's anywhere from 100 to 200 meters plus in a utility project, and I'm going to have some cable losses on this cable. This is simple physics. I can do some things to perhaps try and reduce these losses, but they're going to be there. That means that by the time that that power gets to the AC station, that I've lost somewhere around 1% of that energy that I'm then not able to feed into the grid. So this distributed design ensures that I'm basically never able to feed 100% of my inverter's output into the grid for the lifetime of my project. In comparison, again, the virtual central design at the bottom, because the single-MPPT inverter is centrally installed next to the AC station, I can carry that DC overloading advantage all the way to the inverter. And only then do I convert from DC to AC. And at that stage, I have maybe 10, 20 meters of AC cabling before I'm at the AC station and feeding into the grid, which essentially means I'm always, for the time where I can produce 100% of my inverter's power, I'm feeding all of that 100% into the grid, which of course increases my business case. One last point on what I mentioned before, our Kaco service advantages. Our global service division offers some service points here that to make life for our technicians and our customers even easier. We have a service support hotline that's available 24/7 for any queries or any troubleshooting points you may have. You can talk to a real person and have your query sorted out. We also have a swap inverter concept. String inverters, as we all know, are relatively easy to swap. They're even easier to swap with a central inverter topology. We can provide you some swap inverters depending on the size of your project. and you can have them swapped in the field should anything go wrong with inverter for whatever reason very quickly. We also, however, offer spare parts. Yeah, so if there's an issue with an inverter, it doesn't necessarily mean that it has to be the entire inverter has to be replaced. So whether it's a fan or SPD modules on the DC or AC side, our SPD modules are replaceable. It's even quicker than replacing an inverter. So that's something that we can offer our customers as well. And of course, we offer commissioning support for any of your projects you may have. Again, in total, makes the life of our customers on the after sale side even easier. That's it from me for the moment. I'll hand back to Ronak for a few closing points.
Yeah, I'm going to now not a small but a significant bonus for using the single MPPT inverters is it takes away your headache of matching the inverter and the module together. Now we have seen a lot of different types of modules coming up in the market, and speaking specifically of the high power modules which reach high current levels, some of them working in the range of 12-13 amperes and some of them going beyond 17-18 amperes as well. Now when you're using a multi-MPPT inverter, you have to choose between one of them. Either you work on the low ampere range where you have many MPPT or many inputs, and you can connect the low ampere modules to them and reach the required DC power that you need. Or you choose the higher, the inverter supporting higher ampere modules, which have only a few inputs, high current rating, but only few inputs, and then you reach your required DC capacity. But there is seldom an inverter that would be suitable for both low ampere modules and high ampere modules, and that can be seen within a white paper that we have written. We have compared various inverters, multi-MPPT topology with different types of modules available in the market right now, and seen how do they fare and how is it easy to do sizing with them. And typically you will be underutilizing your inverter most of the cases when you're trying to size with a high power module and a multi-MPPT inverter. Compared to that, using a single MPPT inverter, you have the full flexibility to work with, as you use a DC combiner box before it, and the DC combiner box comes in all customizing options possible. You can choose from 10 inputs, 12 inputs, 16, 20, 24, whatever the requirement may be. You can also choose between the fuse rating, so it could be 15 amps, 20 amps, 25 amps, 30 amps, depending upon the capacity of or the requirement of the module. For the inverter, it's all the same, as it has a high, especially the Kaco silicon carbide inverters have a high DC input capacity. We have capability of up to 300 amps short circuit current, which allows you to do almost 50%, or even not almost 50% minimum, but even higher than 50% overloading. So that gives you the full flexibility to do your DC design layout, gives you a lot of security in this current unsecure times when there could be a lot of supply issues, what module prices you can secure, from which manufacturer, so you do not know. And to secure the design, you have one less thing to worry about when you're using a single MPPT inverter on your projects. So with that, we would like to show some references where we have proved this concept of virtual central with different types of projects in different locations. So the first one is in Norway with the Blue Planet 92 inverter, 2 megawatt project. You can see the rooftop more or less homogeneous. It's a rooftop project, even and done with single MPPT inverter and virtual central concept, also for a rooftop scenario. The next projects that you see following in US and in Turkey, these are ground mount utility scale projects. For the one in between is a 5.3 megawatt block. It is not just one block, but several blocks of 5 megawatt that have been installed for community solar in US. And the last one is in Turkey of an 11 megawatt plant with the same inverter family. Now all of them different locations, different types of installations, different modules, but they prove the fact of ease of use of virtual central concept, which is only possible with single MPPT inverters in the end. we would like to thank you very much for your attention, and we would also then now be open for all your questions.
Thank you very much.
All right. Thank you very much also from my side. I hope you can hear me this time around.
Yes,
Short note would be
Yep.
great. You can.
Yes.
Perfect. Great. I had a little problem with my headphones earlier, and I did want to ask a question to you, Andreas, but you guys handled it like pros, feeling like fish in the water in front of the camera already. But Andreas, there was a question regarding the methodology of the study you did, and that was especially with regards to the time resolution. Maybe you can elaborate a little bit on that again.
Yes, I can. So in fact, the reason for why we analyzed
Andreas,
this
can you
in
hear us?
detail was, yeah, I can hear
Yep.
you.
We can hear him.
Yeah.
We can hear him. Yeah.
Okay. Okay. Good.
You can hear Andreas.
Okay, then I.
Yeah.
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 Okay, I can't, which is not good.
Okay, but I
Not
understood your
very good.
question. So.
I'm thinking that Andreas has answered the question now. There was also a question, Andreas, with regards to the synthetic MPPT reflecting real and physical MPPTs, and maybe you can elaborate how you included that into the PV-SYST model and how you think of the accuracy of including synthetic MPPTs.
So the methodology that we have chosen was that we added the MPPTs, and we have chosen kind of a worst case implementation. So we have chosen the same parameters of the inverter, so the same voltage range, same power range as the single MPPT inverter, but we just increased the number of MPPTs, and in that way, of course, it's not 100% correct because these parameters would change normally if you have a multi-MPPT inverter. But from our perspective, it's kind of a worst case consideration. That's how we did it.
Okay, thank you. Then we have more questions for you guys. So people are asking that if you use a single MPPT inverter and you have a longer DC cable run, wouldn't you have more losses on the DC side? I think, Boban, you explained that earlier.
You would have DC. Sorry, that's actually a point I forgot. You would have cable losses on your AC cable as well as your DC cable. That is correct. But by planning your main cable run with DC and being able to carry the advantage of that DC overloading all the way to the inverter, I can afford to lose 0.5% or 1% on the DC side without it affecting my AC output for the majority of the time, because I'm carrying so much more DC power than I actually need to achieve 100% of my inverter's AC output. I can afford to lose a little bit on the DC side without it affecting my AC output, unlike with the decentral solution.
Yeah. If I may add, the DC overloading would kind of absorb the DC losses that you would have. So you would not see the effect of DC losses because of the overloading on the DC side.
Correct. They are there of course, but they have much less effect on your AC output.
Correct.
All right. And there was also one question that's again for you, Andreas, to ask about the methodology of the study, and it's what type of adjustments were performed on the PV-SYST model based on your model and measured data to make it more accurate. You were going over it a little bit earlier, but I'm thinking there could be a little bit more color and substantiation to it. And also, what tool did you use to model the sub-hourly energy yield? And I think I can't hear you again. I hope my colleague Beatrice will let me know as soon as you finish with your answer.
So I understood the question, yeah. So yeah, the question is on the system that we built with Python, and we integrated in Python more or less the same that PVSys is doing inside. So, and by doing this, so we have chosen also the single diode model. We have chosen the same parameters for the modules, and when it comes then to the reliability of the data, we compared the value from the models that comes from the manufacturer with data that we got from our CALab, and we did then the refit, and we saw a difference. But regarding the result of our study, of course, this has an impact on the absolute value of the yield. So this will change if the module is worse or better. But in this study, that was not the focus to get a 100% accurate yield simulation, but the difference between with multi-MPPT and with single-MPPT. And that was, that represented correctly in PVSys. That's what we stated.
All right. Thank you, Andreas. I have a question from multiple people in a different way, and maybe you can all elaborate on this a little bit. Based on what we've heard today and what we've seen, people would obviously like to know when they're supposed to use a multi-MPPT device and when they're supposed to be using a single MPPT device. And I would add that to that question, that when you modeled the two different systems, you have seen that they were within 1% of each other in terms of yield gains. How many percent of yield gain would you think are necessary to justify the use of a multi-MPPT device?
Yeah, okay, maybe I start. For my opinion, I think 0.5% is already a lot regarding the yield. So 0.5% or 1% could be enough to justify multi-MPPT if you really want to optimize the yield. But I think a point that is also much more important and which is not addressed in the study are the costs of the system. And this is a much more complex question. And so, in terms of yield, 0.5% or 1% yield gain would justify multi-MPPT. But if you plan a system, then costs are maybe one of the most important points. So, and this is not included in our study. So that has also to be included.
If I may add, the multi-MPPT inverter would be used better in place where I have heterogeneous design, different string length, or going to the same MPPT, or if I have a near shading object where we have seen the yield gain in the range of maximum 1%, and all the other cases which are affecting the irradiance of the module would not have that higher impact. So east-west shading or module row spacing, table spacing, wouldn't justify the need to use a multi-MPPT inverter in regards of interpreting the results. And along with that, as Mr. Angel said, of course, the cost of the system and how the topology is built would also affect the decision. So it's not a simple decision, but of various factors. So one point is difference of the yield gain between multi and single MPPT. Then is the difference of the absolute efficiencies of both inverters. If you are compensating that 0.5% by single MPPT inverter, then again you come to square one. And then is the topology of the installation. When you move out of the inverter to the whole PV plant, how is the installation done and what are the costs coming out of that topology? So all these three factors together would bring forth the answer, as in which inverter to be used in which application.
Correct. Maybe a closing comment from my side is, so you need to look at the LCOE, right? So the cost of the capex costs are important. I dare say in most projects, if you really have a 1% difference in yield, and that's a big if, then you would assume that would be beneficial over a 20-25%, 20-25 year life span of the installation. But the question is, do you really have that, right? PV assist is as an important part of the equation, but it's one part of the equation. And we heard from Mr. Hensel that the efficiency of the inverter wasn't included in the study, which would be an advantage for single-MPPT inverters, and of course that the plant design in itself also plays a massive factor in that question of if or do you really have a 1% percentage gain, yield gain at the end of the day.
Yeah.
All right. Well, speaking of plant design, I have one last question that's exclusively for you, Ronak and Boban, and that is asking for a sneak peek into your product strategy. With this in mind, what we've seen and learned today, is there any 300 kilowatt plus string inverter plant from your side?
I think we've got some things up our sleeve. What I think we can say at the moment is that we look forward to seeing everyone into Solar this year. So we'll be making some announcements there. But I think we showed our strategy in one of the first slides. I believe that we believe that for utility scale PV, large scale PV plants, that a single MPPT string inverter topology is the way to go. And as Ronak already mentioned, we certainly not shying away from multi-MPPT. We're not trying to pit the two topologies against one another. It's simply a matter of fitting the application. So we do support multi-MPPT. We do have developments in the work for multi-MPPT as well as single MPPT, depending on the application.
Correct.
All right. Thanks a lot. Thank you for sticking around and answering these interesting questions from our audience. I definitely enjoyed it. I wish I could have heard Andreas, but I also heard him earlier in the German webinar, and I heard him until now, until the Q&A session. There's always a problem, but it's no problem. I definitely enjoyed the session. I hope our audience did, and if they did, I would be happy if they answered our survey. That would also help us to, in the future, produce more relevant content for them. And also, I would like them to welcome them back to one of our webinars. We have a new magazine out. That's also good. We have more webinars coming up this year, obviously in early March. Going on, you can always check our website under the events rider button. You will find the webinars. You can also do that, obviously, on our different language websites. We have French webinars and German webinars, and I think occasionally also Spanish webinars. So thank you so much for staying around and joining this webinar. I hope to welcome you back soon. Thanks again to Andreas, Ronak, and Boban.
Thank you.
Thank you.
Thank you.
Thanks a lot, and bye-bye.
Bye-bye.